Okay, let's see. That should be going. Um, so yeah, before we get into the class today, we're gonna be talking about prefetching. Did everybody see the announcement yesterday about alternate projects? Any, I don't know, thoughts, questions, concerns about that? Um,
I actually have a question.
yes.
Um, so I know me and my group wanted to attempt assignment two, but at the same time, we don't know if we'll have enough time to completely fledge out the project. Is it possible to basically do alternate assignment two, but instead of the term paper, do like the project that's entitled in like part three? So do assignment two for 30 points and then do the the paper project for 80 points. Is that a possible combination?
Sure. Yeah, I mean, I don't see why not. I mean, it's gonna be a lot of work, but if you're up to it, sure.
Okay. Thank you.
Uh-huh. Yeah, I mean, you can choose any combination, of things, and if somebody has an idea for something else they want to do that kind of fits the scope, I'm happy to talk about it as well.
Makes sense. Thank you. I'll run. Do you want topics for the papers run by you in the project proposal? Is the project proposal just which one are we going to do?
Um, I think it might be a good idea to pick something and then we'll talk about it. Yeah. So in the project proposal, I do want at least a brief outline of what you're gonna tackle.
Okay, sounds good.
Because otherwise, we're already into the last month. You're going to have 1 month left to do all this, and got to make sure. I want to make sure that you're not chewing off too much.
Hmm.
Right, so it's actually possible.
Yeah,
to do the work.
that makes it. I think just in my mind, I would rather do the project that's attached to part three because it seems like a little bit more academically structured.
Mm-hmm.
But yeah, that was just my thought process on this.
Sure. Makes sense.
So if we do option one, do we still continue? Is assignment two still worth 20 or 30 points?
Yes. Okay. So the cash is still worth 30 points. It's now the project will then be everything but the cash.
Okay.
So the rest of the
cash is subtracted out of the original 80 points for the project.
I wouldn't say subtracted. The 80 points for the project, well, if you go, the base project's 50 points, right? So that 50 points is still for, building the 5-stage pipeline. Just before it was the core and the cache, now it's just the core.
Okay, so how much, well, for example, if we only did the 50-point project originally, if that was our proposal, and we want to do assignment two and the project, then how many points can we get for the project?
50, plus 30 for the assignment. That's what I'm saying.
Okay.
The cache is no longer part of the project.
I see. Okay.
It's the assignment, and well, it's a bit of a catch-22 because you can't really build a core without a cache. But
yeah,
their point structures are separate as well.
Sounds good. Thank you.
All right. Yeah, so feel free to send me email if you have questions. I'm not holding office hours at a fixed scheduled time slot because that's like nobody really shows up historically and it's kind of awkward. But I'm happy to, schedule them ad hoc. Just drop me an email. I will pick a slot. Also, in your email, send me a slot availability, right? So I don't have to. So I could just see if anything works for me or suggest alternate availability. Yeah. Okay. So yeah, if you know if you have other questions, let's I don't know, put them on Piazza or bring them up at the end of the class. Either way is fine. So let's get into this. So we're going to be talking about prefetching today. Um, uh, you know, why would you want a prefetcher, or what would you be prefetching? Somebody want to take a shot? What does prefetching mean to you? And in the context of the class, we've already dealt some in, like you looked at, you kind of got an overview of it for assignment 1. So somebody want to rehash what we learned there? Nobody? Okay, am I recording this? Let me check. There we go. Yes, we are recording. Okay, so since nobody wants to take a shot, let's dig into this and see what we get. The idea of prefetching is to fetch a block of data ahead of demand. You are going to make an access to some data at some point, and if it's not been accessed before, it's unlikely to be in your cache, and so you're going to have to pay the full access cost, right? So you're going to have to walk L1, L2, L3, whatever else, and then go out to memory and wait for the entire time of having to wait there. And these, if you can shorten that period of time that you've spent waiting for data, you can obviously finish computations faster. So typically we saw that there were a couple of different types of misses earlier: compulsory, capacity, coherence, and conflict. Prefetching can target compulsory, capacity, and coherence misses, although you've not quite seen what coherence misses are yet, but not conflict misses. Why can't it target conflict misses? Somebody want to recall what a conflict miss is, or what a compulsory, let's do all of them. What's a compulsory miss in a cache?
It occurs when the information is first brought into the cache. It's compulsory.
Yep. So there's no way to skip that. What is a capacity miss?
I do not remember.
Okay. Somebody else want to try?
I mean, capacity, is it when there's not enough space or something? Like you can't load all the data?
It is a capacity miss does occur when there's not enough space, but it's not that you can't load data. It's that you tend to you flush out old data that that's least recently used, or whatever your flushing policy is. You remove that data and you insert new one. And so when you try to access the recently removed data, you get a capacity miss. It's a miss on something that would have been in the cache if the cache were larger. That's a capacity miss. A coherence miss is an event that, when you don't find something in your cache because another processor wrote to the same, or read from, or took an exclusive block on that piece of data, and so it was bounced from your cache, we've not looked at this. We will look at them later when we look at multi-core and cache coherence. What is conflict miss?
Is it when you have the set associated cache and the same tag is mapped to different sets? Or rather, there are already pieces of data in those corresponding tags?
Well, I think you're using a term wrong there, but yes, a conflict miss is when you were forced to remove a piece of data because your set is full, right? You had a new piece of data come in that went into the same set, and all the ways of the set were full. So you had to remove one of them and put the new data in, and so then you get a conflict miss. It's kind of similar to a capacity miss, but it isn't. It also is kind of sometimes you get conflict misses when more than one process executes on the same core and they could have the same data that hits, the same address. Anyway, so when you're doing prefetching, the big challenges are knowing what to fetch. So, if you go out and fetch blocks that are not going to be used, you've just wasted resources by keeping that data around, and the prefetching has to be implemented somewhere. So that whole process was a waste. And then you have to know when to fetch, right? So if you do it too early, you're just gonna clutter your cache with useless data, and then it's probably going to get removed before it had a chance to be used, and then you've just wasted cycles and space and lost performance because other instructions data was also kicked out by the data you brought in with the prefetcher. If you fetch it too late, well, there's no point to. You're not prefetching if you don't have the data available by the time it's used, because at that time it just becomes a demand fetch where you're blocking an instruction. Typically, fetching too late tends to be better than fetching too early, because at the very least, when you fetch too late, you've already front-loaded a portion of the demand access time, right? Like if it took, I don't know, 10 cycles to walk, the L1, L2, L3, and go out to memory. I don't think there's such a machine has been built for a long time, but let's assume that, right? Like 10 cycles. And if you fetch too late and you've already issued the fetch to memory, and you're in the 5th cycle of that access time. Now your instruction that wants that piece of data only has to wait 5 cycles, as opposed to having to wait 10 cycles. So fetching too late, unless by too late we mean, the prefetcher is not in sync with computation and it starts fetching something after the computation's done, then that's kind of pointless. But yeah, so these are the two things that you need to do to prefetch. But let's concretely look at why we do prefetch even, right? So if you didn't have prefetching and you were just doing a load, you check the L1, right? It's not there in the L1, so we go to the L2. It's not in the L2, and we go to DRAM. So that's the total time it takes to fetch a piece of data. This is round trip time, right? Not just sending the request out, but receiving the data back as well. So this would be called the total load to use latency. Now with prefetching, you'd hope that you could do this, right? Where you've brought in the data with the DRAM read and all of that earlier, ahead of time. And then when you go to access that data to be used, you only have to traverse L1. So you have this much smaller load to use latency. Now that's perfect prefetching, which is that you've brought the data in, you put it in the L1 ahead of time and everything. Sometimes you don't get that. You get something like this, which is that you've gone through some portion of the the DRAM access, and then when you actually need the data, you check L1, you check the L2, and you realize that the memory request has been made, and it returns quickly than it would if you had to wait for the whole thing. So this essentially means that if you were to if you had a bunch of loads in a row and you were to be able to prefetch each of them, then you've kind of if you stack these together, you've reduced the total latency from this much to whatever this is, one after the other, right? So you always see a win. Now that there's kind of an implicit assumption here. Does anyone see it? When would this work, right? When would this whole thing work, and when would it just be a bad idea?
When you're actually going to be using that data later.
Yes, that is true. So that's one, when you're fetching the right data. But there's another one that's more of a hardware constraint. DRAM accesses take some resource, right? Like you have to have a DRAM scheduler, you have to have a bus that connects between the DRAM and the memory controller, and the DRAM operation takes a certain amount of time, has a certain control logic resource, and all of that. We saw this in the memory class, in the memory lectures. So what could go wrong? What's the assumption here?
I think you're just assuming that it's already, or the DRAM is not in use when you go to prefetch.
Yes, you should. Prefetching should never prefetching should never take higher priority than a demand access, right? So the only time when a prefetch is useful or can be done is when the DRAM controller or the memory controller, whatever, has slack, right? When their CPU is not otherwise issuing a demand fetch for some data, and you have some slack cycles that you can then squeeze in a prefetch or two. Otherwise you would be kind of slowing down other parts of the part of the computation that's actually executing at the moment, and that's not a good thing. We'll see how this is kind of maintained naturally, right? So typically it must be accurate and timely, and it also must not trample other requests. So just another way of thinking about this, perfect prefetching would allow you to kind of execute the program without having these waits in between that are waiting, where it's waiting for loads to occur. So if you could do this, then your program could just run without these blocks in between, and so total execution time is much shorter. Right, so in some sense it's removing loads from the critical path. What is the critical path? Somebody want to remind the class? This is the critical path for a program, not a processor. What is the critical path? You may have heard of the term critical path during discussions of locks, synchronization. It's the same idea from that. Nobody wants to take a try? You don't have to be right. You can just take a shot.
Does it have to involve what resources have to be acquired in what order to make sure nothing's locked up?
That's, I wouldn't call that the critical path. That would typically be a locking order, or there would be a locking safety thing. But the critical path is just a term that refers to, in locks, for example, the work that is done under the lock, right? So whatever you hold, whenever you hold the lock and do some work, that is typically called the critical section or the critical path. The same thing here applies slightly differently, which is that it's the time, it's the time that's spent doing work, right? So it's work that you cannot parallelize in some sense. It's work that has to occur in this order. So by removing the loads from this, whatever, like without prefetching, the load is on the path of execution. You cannot do anything about that. You have to stall the program and wait, because that instruction needs data to execute, right? Or some set of instructions need a particular piece of data to execute. Now, so it's a similar idea. Maybe I'm just kind of digressing, but I don't know. Maybe I thought that might be helpful. We'll see. So yeah, common types of prefetchers. There's software prefetching, where the compiler or the programmer puts in instructions to go, to instruct the memory fetch units to go and bring in some amount of data. And then there's, a bunch of different types of hardware prefetchers. The simplest ones are, the next line, the next end line, which is if you bring one cache line in, it might bring the adjacent cache line in as well. So if your cache line 0 comes in, it might bring in cache line 0 and cache line 1. Next end lines is, instead of bringing just 0 and 1, you bring 0 to, I don't know, 5, something like that. Then you have stream buffers, which are used to bring, which are used to fill the cache when you're doing a streaming computation. So if you're trying to walk through an array and access each element once and add it, let's say you're doing a sum over an array, right? So now your access is actually kind of streaming. You never really go back to earlier data, and you just keep going forward. So you can detect that pattern and prefetch ahead of time. Then you have stride prefetchers, which are like they observe that you're accessing data in every second or third or fifth cache line, and then they bring data in at that granularity. These are all like when you have within data patterns. I guess localized also is kind of a stride prefetcher, but PC based. We'll look at that later. And then you have pointer based prefetchers, which try to help speed up accesses to linked lists or trees or graphs. So any data structure that depends on pointer accesses. And then you have a thing called correlation that we'll look at later. Yeah, so we're gonna spend a couple of I think the rest of the class looking at each type of prefetcher. But before we get into this, questions about what prefetching is, and did that make sense till now? I don't know.
I had a question. If you go to the timeline slide,
This one?
maybe one before that.
Okay.
Yeah. So you issue the load, right? And then at some point it sends back the data. So is that data stored in a cache at some point, or is it just directly mapped into like wherever needs it?
So that depends on how you choose to implement it. You can be implemented both ways. Most processors that you see today will implement their prefetchers in, there'll be one type of prefetcher between memory and L3, another couple of types between L3 and L2, and then a different type between L1I and L1 data. So necessarily they're prefetching that way. That said, there are software instructions to prefetch a certain type of data into a certain register. So you can also prefetch that way. So yeah, depends.
Okay, thank you.
Other questions? I'm assuming, I'm going to assume that people don't have any questions because we've not covered much till now. So let's have a look at what software prefetching would be. So software prefetching, is when the compiler or the programmer places instructions into the source code to fetch data ahead of use, right? So now this data can be prefetched into a register. This is called binding or hoisting. But then it might prevent further instructions from committing, right? Because you've prefetched a different value into this register, and instruction before, like an instruction that's currently executing may have wanted some other value that was in that register or whatever. So you're slowing things down. But sometimes this is useful if your computation is small enough that, or you don't use too many registers in your computation, then you can actually keep a set of these registers to use as prefetch targets and then manage computation that way. Most of the time, data gets loaded into the cache. This obviously requires ISA support, and may get evicted from the cache before a demand, before it's used. So this could be an example of this would be like this, right? Like so you had this program R1 in this section. R1 is equal to whatever is at the memory address pointed to by register 2. So now that's going to be a cache miss. So these, another thing I should point out is these are, blocks of the program. So this is one basic block or a function. Let's say this is a different function, there's a different function. And when you call them, it branches out, right? So there's a control flow graph. Now you could place the prefetch R1, equals the thing at R2 in A, and then, do the access in C, right? So here you're hoping that the load is serviced, the miss is serviced by the time we get to the consumer. So this is what you would call hoisting. A lot of compilers typically do this kind of hoisting, inline, like they do it all the time. the only issue that you must be, like, the compiler needs to keep track of is that, there isn't a dependency that would make this hoisting invalid, right? Like if you had R1 equals R1 minus 1, and you loaded R1 equals R2 at the top, before that instruction, that would actually, you'd end up with the wrong value of R1 for this R3, for this computation. And so, that's, keeping track of that is important. So that actually just makes it, so hoisting is typically done, and most compilers typically depend on heuristics in that they'll try to hoist something up to a certain complexity. So if they suddenly have too much state to keep track of, they just say, okay, I don't know what's happening. I'm not going to hoist this, and leave things as they are. So most of these kinds of optimizations in compilers tend to be heuristic dependent, which is they go up to a certain point and then say, okay, I don't know what's happening, and just bail out. The other type of prefetch software prefetch that we were looking at is programmer written prefetch. So this would be prefetch R2. The instruction is literally called prefetch, and use it. If we were to issue that, that would just get loaded into the cache at some point. We don't care, and then when you try to access this, you're hoping that that piece of data is still in one of the cache hierarchy, somewhere in the cache hierarchy, and then the access, hits in the L1 cache or the L2 cache or whatever. So in this case, you can avoid data dependencies because you're not fetching anything into an instruction. But then you do run the risk of the data being eliminated from the cache before you use it, and then I guess it becomes even more complicated as to how do you figure out how far ahead do you prefetch something, right? Like when do you insert that prefetch instruction? When does it make sense? How do you figure that out? That actually becomes a really hard thing. So an example of how to use this, you had a for loop that walked through like a 2D matrix. So I is rows, j is on columns. So you can prefetch the next row, right? When you are doing something with the row that you're currently working on. The pro of this, I mean, the benefit of this is that the programmer has complete control and flexibility, so it allows the programmer to put in these hints when they have studied the program very carefully and they know what to do, and they can't get the compiler can't get this right. Like there's some cases where it's just too complicated and your compiler is not able to get it. Hoisting happens either way. So prefetching, putting in prefetch instructions gives you that flexibility, but hoisting also happens in most compilers, all at the expense of compile time, and there's no additional hardware support needed for either of these. The prefetch instruction needs the ISA needs to provide an instruction, but you don't need to change much else. The downsides of software prefetching is the fact that achieving good performance is now a thing that the programmer has to take care of, or the compiler has to take care of, which becomes really hard because how do you do something like this example that's here that says if you have an instruction per cycle target of 2 and 100 cycle memory access latency, you've got to move your load 200 instructions earlier than when you're going to use it. How do you determine when 200 instructions in the current function are? What if you don't even have 200 instructions in the current function, right? Hoisting has some idea of, the compiler has some idea of when a certain number of instructions have occurred, and might be able to do something like a hoist out of a loop, right? Because you're assuming that the loop runs a certain number of times or whatever, just heuristic dependent. But if you're a programmer and trying to put in that prefetch instruction on your own, it's really hard to figure out when the right thing to do, when the right thing is. So typically people tend to do this. I mean, you might at some point actually end up doing it if you're writing some really performance critical code. Examples of such code would be crypto code, if you're writing a library for some embedded system, if you're doing like, I don't know, camera work, like you're working on something like a camera or stuff like that, or you're building a really high performance algorithm for, I don't know, DNA, base calling, something like that. People typically run the software multiple times, collect a trace, look at what kind of lead time you need for the instructions, and then manually go in and like manually plot out where you can insert things, and then go insert them there, and then hope that the compiler doesn't optimize away or mess with your reorder the instructions. Right, so the downsides of prefetching, other downsides of software prefetching, is that if you keep prefetching too early, you may actually lead to very low accuracy and then cause other kinds of problems, because the program may not go in the path that you think it's going to go in, right? Like if in the example earlier, we saw that there was A which could go to B or C, and if you were prefetching data for C in A, but you always ended up in B, then that prefetch is useless, and it could even harm the performance of B, because the DRAM access time could be longer than the time taken to execute A, right? And that also means that, prefetching, if you insert the instruction, could also increase the code footprint, which means more iCache misses, and iCache misses are really, really bad for performance on most CPUs. I think every few percentage miss rate increase, you see like, I think about a 10% increase in iCache miss rate, and you'll see a doubling or 50% increase in performance, 50% decrease in performance, things like that. So iCache miss rates tend to be really, really important. Yeah, and you could have code alignment issues where, because you're now this doesn't occur in most RISC ISAs because instructions tend to be 4 bytes long, but on x86, where your instruction could be from 1 byte to 15 bytes, inserting more instructions means that some things may get misaligned. Yeah. So as an alternative, so software prefetching still exists, right? Like we still have prefetch instructions. There are a couple of them: prefetch A, prefetch B. I don't remember what the difference is, but they tend to be used in very specialized situations, and most people, don't really look at them. We mostly rely on hardware prefetching. Hardware prefetching is where the hardware monitors memory accesses, looks for patterns, and then it guesses that this something that there's some pattern here, so let's go prefetch data that is further along the pattern. So usually you put something into a prefetch queue. The queue is checked when there are no demand accesses waiting. So when the DRAM controller has a few slack cycles, it goes and checks the prefetch queue, brings those things in. Prefetchers just look like, the prefetch queue requests are just read requests. You may sometimes see a special prefetch flag in a cache line, for example, and that's primarily just there to to provide a way to give feedback to the prefetcher, whether did the prefetch work? Are you doing the right thing, right? But it's strictly not necessary. Whereas for the memory hierarchy, it just looks like a read request. And so, yeah, prefetchers are one way of trading bandwidth for latency. If you're guessing accurately, you're using no extra bandwidth. You're using spare cycles. If you guess incorrectly, now you need to fetch other data, the correct data again. So then you're using extra bandwidth. And latency reduction happens only when you guess correctly. If not, you got to wait for the full cycle. So the benefit of hardware prefetching is that you don't need to change software. So how does this look, right? So let's say this was a processor organization. So the top here we have the core. Like, we're not showing most of the pipeline, but let's say we have we're just showing the data holding stuff. So you have registers, you have the L1 iCache, Dcache, and their respective TLBs. You have the L2 cache, the L3, and main memory. Where would you put? What are all the potential prefetcher locations? Like, where could you build a prefetcher? Assume a prefetcher is something that keeps track of memory accesses, tries to guess a pattern, and then builds a queue of prefetched of addresses to prefetch. So that's kind of the block that you would be building. Where would you put that? Where could you put it? Yeah. Go for it. Where was?
I mean, what we talked about before seemed like it should go in between each level of cache or memory. So it's sort of like a cascading effect.
Sure, that is correct. You essentially have, all the potential interfaces between one level and the other. That's where you would kind of place a prefetcher. And the prefetcher, each of these prefetchers kind of fills the table or the structure above and reads from the structure below, right? So whatever's filling the registers here fills, like these two fill the registers, but only look in the L1 cache. These two look, fill L1 caches, but only look at the L2 cache. Same thing here and same thing here. So you'd kind of have a cascade, as he said, of, if the prefetcher misses here, then this prefetcher takes over and looks here, tries to get the thing from here. If it's not here, this one takes over and looks below, right? So yeah, most of the time you have multiple prefetchers, usually close to the core, and then you sometimes have prefetchers and the L3. It's easier to do at the core, to detect patterns at the core, because its accesses are right there, and that's all you're looking at. And the LSC, L3 or whatever the last level cache is, they tend to be a lot harder because the cache itself is not one entity; it's multiple banks, and each of those banks has its own controller. So you might have to essentially build a prefetcher for each one. Then you're no longer, it's hard to see a pattern because accesses could be going to different banks. And then other things happen, like you have multiple CPU cores, and all traffic from all of the cores is kind of going to all of the banks. So it's a little harder to see patterns there. Although sometimes you get lucky, and if two threads are working for the same, if all the cores are working on the same program, and there's some pattern that kind of some kind of strided pattern across all of them or whatever, then the prefetcher might be able to do a good job in the last level cache. So let's look at what these prefetchers concretely are. There's the simplest one, which is the next line prefetcher. On request for line X, prefetch X plus 1, or more generally X XORed with 1. So if you're fetching an odd one, you get the even pair, and if you're fetching the even 1, you get the odd pair, right? So this is the next. You're trying to form a pair. This is good for spatial locality. So if you're trying to access things from one line, you're going to access things in the next line. It is often a good assumption, except when you're trying to do a strided pattern, in which case, if you're accessing like nth byte in every line, or in every nth line or something, then it's a waste of time. It's a waste of load. It used to be that you'd stop at a physical page boundary. So because most of your accesses are virtually indexed, most of your caches are virtually indexed, you would stop at when you crossed a page boundary, a virtual page boundary. That has changed. There are actually prefetchers since 2014-15 onwards that actually walk the TLB. They access the TLB and check what the next physical page is and start prefetching from that page. That one, I think, is called the next page prefetcher. Yeah. So this actually is pretty easy to implement because it's a single XOR operation on the given address, and then instead of issuing one read for a certain one read for a certain size, you just issue 2 reads for that size, or if it's possible to read a larger size, you issue a larger size, right? And then the benefit of accessing such a large thing is that the DRAM row buffers tend to be quite large, and so you can use a bursty access from the DRAM. This works for both iCache and Dcache because instructions execute sequentially in blocks. When you have a jump, of course they don't. And it also works for the Dcache because a lot of big data structures span multiple lines or blocks or whatever. Yeah. So the benefit for most next line prefetchers is actually minimal. They're kind of minimal in that they only work with, if you fetch one line, you get the pair of that line. So yeah, it is. You're not going to fetch the thing after that line, for example, right? So that kind of has a, at best, you've saved 50% of the loads, which is not nothing, but yeah, it's not as good. So then you can have a simple modification on this. This is the next end line prefetcher. So if you ask for line x, you get x plus 1, x plus 2 until x plus n. N is the prefetch depth. And it's important to make sure that your prefetch depth is not too large. Because if you go too large, you might cause capacity misses and cause performance problems in the for other instructions. And then you're just you need to the deeper your n is, you need to have a deeper prefetch queue and a place to store more of these lines if you don't store it in the cache, right? But if you have a streaming access pattern, or if you have a simple localized access pattern, a larger n is good for performance if you're accurate, right? So how does this work? I guess we're going to look at a stream buffer, and then we'll see an example of that. So stream buffer is it takes the same idea of the next end line prefetcher, but then says, what if I have intertwined streams, right? So if you had A, B, A plus 1, B plus 1, and so on, the way to, like, you could use multiple end-line prefetchers or multiple stream buffers to track them. So you keep next n available in each buffer. So one buffer tracks one stream, and you just have n of those, and you can track n streams. And so that's how it would work. You can also kind of do a slightly sort of sequential or quasi-sequential stream buffer, which is on request y in x to x plus n, you can advance by y minus x plus 1. So this allows for a slightly different pattern. It's still kind of stream, but you're kind of jumping around. This allows the buffer to work when certain items are skipped, but then it's also expensive because it requires associative comparisons when you're trying to do the access. So how does this look? So this could be, you could think of this as how to implement a stream buffer. And we're using stream buffer here as a general category for next n prefetcher, right? Like whether it's the next line prefetcher, the next n line prefetcher, or a next block prefetcher. They're all kind of special cases of a stream buffer. So this was, the cache, if you were to imagine a cache hierarchy, right? So if this is a direct map cache, you get an address from the processor, you use that to index into the cache, you have some tags and data, and then you return the data. Now that's we've seen that before, it's not what we're interested in. And then you would have this this additional data structure here called a stream buffer, which is really just a FIFO queue, right? Or at least in this case, it's FIFO queue. And the address goes to that as well. So you have a comparator, you have a tag and a comparator, it compares against all of the available tags and then returns whatever cache line of worth of data that it has, loads that into the direct map cache, and moves forward. Now, the key to note here is you're essentially using this to load future access data. So you won't load data for this address, you'll load the data for n plus 1 or n plus m or whatever the thing was. And then you have a different, some control logic down here, which also, fetches data in that pattern from the next lower cache or memory or whatever. So the same stream buffer could be implemented. You have multiple stream buffers to track different streams of data, and they're essentially just replicated, but they all kind of use the same lower cache access infrastructure and then write into the same upper cache. Right. Any questions on sequential prefetch till now, essentially? Okay, I guess nobody. I guess, is this clear? Are people lost? Is it more that, this is fairly obvious stuff and so nobody has questions, or? Okay. Maybe someone's trying to say something, but their mic's muted. No. Okay. So that was, sequential prefetchers, right? Like they're all going one after the other. They're accessing data sequentially. You might also be accessing data in a stride-based pattern, right? So then you need something that detects that stride-based pattern and then loads data in that pattern. For example, if you were accessing only one column in a matrix, right? This is how the data would kind of be laid out one after the other, and then you're accessing that piece of data, right? Oh, sorry. Yeah, if these were an array of structures or whatever. So the prefetcher essentially has to realize that, hey, there's some pattern here. The pattern here essentially is X, which is the index into the matrix, plus some offset, right? And then X keeps increasing, but the offset stays the same. So it could be, the notation used here is X is the offset and S is the index, but whatever. And so that's one way of looking at it. So how do you, build the stride prefetcher? You essentially, looking for that kind of a pattern, and then you go and prefetch some n sets of those lines. Now, how do you determine whether the stride is, how do you determine if there is a stride, right? So how do you know if A goes A of I, the next thing is going to be A of I plus 1 or something else, right? You typically have to wait to see a couple of iterations of the access. So, when A of I goes to A of I plus 1, that doesn't really give you enough information. Whereas when you see that, it goes to A of I plus 2 after that, now you've determined the stride to be one element at a time, right? So then you kind of figure out how to access that. So the prefetcher essentially is something that guesses certain stride and keeps track of the number of times you've seen that stride. So you'll see you'll have a couple of different counters that are counting for different strides. And when one of those strides kind of increases the count, or the number of times you've seen that stride grows greater than some limit, here we're saying it's 2, at that point we issue the prefetch, because then you have some kind of guarantee. And if not, you update the count. So the way you would kind of see this looking is, you'd have a table that looks like that. And this is a different example. We'll come back to this example, but if you ignore the tag, you would have a table that looks like this, that has some address and a bunch of different strides, right? And it would keep track of different strides and the counts, and one of those is going to be right, and use that. Now, you typically see like common patterns, which is 1, 2, 3, and then some set of powers of 2 or whatever. So yeah, we'll come back to that example in a second. You could localize your stride prefetcher. What this essentially means that you have a stride prefetcher that is able to handle multiple interleaved strides. So if you had you were accessing 3 different arrays, and you access the first one and the second one, whatever, right? Like in one iteration you access these 3, and the next iteration you access these 3, or whatever the pattern is. Then you need to like, if you looked at them all as one, then you would see no real stride. But if you were able to break them up by PC, like you had this one load, another load, and then a store or whatever, then you would essentially see a pattern, which is that you go a plus n, a plus 2n, and so on, and then x plus n, y plus n, and so on, right? So you're able to see a pattern there, and that allows you to prefetch. And the trick here is, of course, that we're indexing by PC, which is where you get this table. So you're going to store a tag, at least, maybe not the PC, but a tag, and then the last address that was used, the stride, and a counter. Now, when the count goes above a certain minimum count, you prefetch last address plus the stride, and it's indexed by the PC, so you get a different, or you hope to get a different stride counter
Professor?
for each one. Yes.
I'm sorry, I cut out. Could you repeat that last sentence?
Which one? What was
You're
the
talking about when it goes above
indexes?
Yeah, index.
Okay. So for each of these PCs, right, like so for each of these instructions, you have this prefetch reference prediction table, as it's called. When you have a certain PC, you index into a certain set of counters or whatever, and the counter might be, it'll store the tag so that you know that you're accessing the right counter, right? Like, so it's not a counter for somebody else that you've got then you have a conflict, and you just don't do anything. You don't do a prefetch, or you replace it depending on what the policy is. But you also store the last address that was accessed in the previous access, and the stride that you've detected. So as long as your count, and this count, and an account, right? And the count increments every time you see the same stride. But you want it to be you want to see it at least twice before you're sure that the stride is valid, that the stride that you think is there is valid. So once the stride exceeds some minimum, the count exceeds some minimum count, you can then issue a prefetch for last address plus the stride. So if some address here was a plus 3n, now you can, and you've seen that stride pattern at least twice. every time you index into this table, the prefetcher, the prefetch queue gets a new address appended, which is a plus 4n. Next time would be a plus 5n, and so on. Does that make sense? Is that
Yes, thank you.
clear? Okay. Yeah. So the prefetch kind of in this structure, at least, the prefetch is happens when you previously load. When you execute that instruction, the next data that would be used by the same instruction in the next iteration of the loop gets prefetched. Yeah. So so we've seen till now, we've seen two types. We've seen the sequential and we've seen a strided prefetcher. But these all are for data that's sequentially laid out in memory. But you can have other data that is not sequentially laid out in memory, right? So there's a term here called regular. Memory access patterns are said to be regular if they have, or memory accesses are said to be regular if they follow a pattern, right? Like, so if you access every second or every fourth or whatever, then you have a regular access pattern. If you're jumping all over memory all the time and there's just random, if you're approximating a randomized memory access, then it's typically said to be irregular, in case you hear the term. So a linked list tends to be a regular access pattern because you're accessing, something like this. But in actual memory, there's no stride because the data could be all over the place, right? Like your nodes may just be, scattered. So how would you access this? How would you prefetch accesses to this kind of structure? So this is important for lists, trees, graphs, queue, whatever. Maybe not a queue. A queue tends to be sequential, but depends on how that's implemented. Somebody want to take a guess as to how you would do this? Okay, let's start with a simpler question. What is a link? What is the basic unit in a linked list or a linked data structure? What is that? It's a data type, right? Like, what does the data type contain?
Are you asking about like what the node contains?
Yes.
So it usually will have some type of data, whatever you're storing in it. And then depending on if it's like a backwards or single linked list, it will have like a next field that points to the next node, or maybe a previous field that points to the one behind it as well.
Okay. What differentiates the two pieces of information that are stored in that node? So you said there are two things, right? There's data and then there's a pointer. Can you differentiate between these two? Like if I just gave you a dump of memory, right? Like some place that stored a linked list, for example. It was just a dump of memory, no real information. Can you tell me, what the node size is, for example? Do you think you'd be able to do that?
I mean, you could try to like piece together the pointers and like kind of make a trail through that way, and then see the size depending on like kind of how the frequency of like by seeing where your trail ends, basically by just looking at the pointer data.
Yes, so that would give you the size of the full list or the full tree. I was actually asking a much simpler question, which is, can you detect the node size? Just one node. Or maybe I understood the your answer wrong. Well, okay. I think maybe I misunderstood your answer. I thought you were talking about a full. I thought you were talking about following the pointers until the end of the list and then figuring out the whole list size. I was just saying one node. How do you detect one node's size? Let's just look at an example of how you do that, right? So if this was a cache 512 bits of data that's loaded into a cache, and this was what you were given, could you tell me what looks like a pointer here? Okay. Does this one look like a pointer? The first one doesn't quite look like a pointer. Well, okay. All right.
I was saying the very large numbers.
Right. So you typically could look at pointers, can look at like large numbers and say, hey, that might be a memory address. Especially since a lot of pointers tend to be 64-bit. I mean, they may have a lot of zeros, but most addresses tend to be pretty high up. So you can look at these two and say, hey, maybe these are pointers. There's a really good way to check, which is, maybe it's around your current data, the data that was brought in, like the one that holds this in this piece of data. These pointers might be somewhere around there nearby, in which case, that's a good idea. And then the other check, I guess, is, if you passed these addresses to a TLB, do you get back yeah, hey, that's fine to access, or is there a violation of like, I've never seen that? If you don't have a TLB mapping for this, you probably want to stop there. So this, using that heuristic, you might actually be able to walk through a loaded piece of data, look for things that look like pointers, and then check with the TLB, is this a valid pointer? If it is, then issue a prefetch request to that pointer. Now, this typically helps you a little bit for things like trees or linked lists, right? Like pointer-based data structures. Pointer-based data structures tend to be really hard to prefetch otherwise. Somebody want to take a guess as to why? And you just saw this in assignment 1, so you should actually know.
Is it because they might be stored in different locations? They aren't all contiguous?
I mean, it is because they're stored in different locations, but there's something else as well. Even if they were contiguous, well, if they were contiguous, your next n-line prefetcher would kind of help you out. But yes, when they're not contiguous, it becomes really hard. In both cases, there's no way for there's no way for you to know other than getting lucky with the sequential. Well, the key thing is that with a pointer-based data structure, you have no idea where to go, because every preceding lookup depends on the previous lookup, right? So if you had a structure like this, the struct bin tree node, whatever, you would not know where to traverse next until this node is loaded, and then you have left and right to look at. So because of that, the look ahead that you can do is actually very limited. You kind of can go, some small amount of depth ahead. If you were to start up your prefetcher like much earlier when you first see the root node loaded and somebody's doing some large amount of computation on that root node, you might be able to, load both left and right and follow their left and rights and so on. But typically, if the amount of computation you're doing is small, then you won't even have enough time to do that, right? So you kind of end up with something that looks like this, which is, if a stride prefetcher can do this, where you access some piece of data, it immediately issues the load for x+1, so that the access latency is kind of, pipelined neatly. A pointer prefetcher actually ends up with this, which is you can't issue the prefetch for the next piece of data, for B, for example, until the access latency of A has finished, because you don't know where B is. And so this is kind of what you get. So if your computation fits nicely into this section, then you're good to go. The prefetcher helped you out, effectively reduce the latency to nothing. But if your computation is much smaller, then you're still paying that time anyway. But yeah, the pointer prefetching typically tends to be really cheap to implement, because all you're doing is adding a little bit of logic to test each piece of data as it gets loaded, and then using that to populate a prefetch queue, so it tends to be very, very easily implemented. Another way to look at
We are over time.
Oh yeah, sorry. Thanks. Okay, we'll stop then, and if anyone has questions so far or something about the project or whatever, I'm here to.
Can we start at pointer prefetching next class?
Can we start where?
Can we start at pointer prefetching next class?
Yeah, sure.
Okay, thanks.
Okay, I'm going to stop the recording.